rather than explaining in immense detail why everything in Andre's talk was totally correct, for the uninitiated but curious about you, I thought it might be more helpful if I zoomed out a bit. There's a risk that I'll zoom out too far, and so I might trespass on areas that you're much more expert on than me. But I'm going to keep tally of a sort of wish list of questions and problems and kind of loose ends in this area. The big theme is positive functions. So we've just seen a whole bunch of those in Ross's talk just now. If you take his canonical form, right, for your region, which is a semi-algebraic set defined by some polynomials, then those are positive functions on this semi-algebraic region which blow up at the boundaries of that region. There have been some other examples. So in cosmological wave function story at tree level, those functions are also this type of positive function that blows up at the boundary. These are called canonical functions. And I want to highlight a few examples so that I'll come back to in this talk. So for example, the second semantic polynomial, when you're doing integral, then this is a positive function in what's called the Euclidean region. The Feynman integral that you get, let's call the kinematic parameters S, then the Feynman integral over the positive projective points looks like this, which doesn't depend on the kinematics, so this is some polynomial, and then second semantic polynomial does depend on S. Now, if you're in the region, which is in general, just like in Ross's talk, it's some region defined by some higher order polynomials, then this function is also positive. So the Feynman integral is a positive function. Actually, a lot of amplitudes, as we will see, are also positive functions in similarly curvy regions. That's one of the things that this curve integral picture from Andre's talk makes manifest. And then I'd just like to give a third example of a positive function, which is the Veneziano amplitude for 4 points, right? So if we look at the beta function, then this is in the ST positive orthant, this is a positive function, and it blows up on the boundaries, okay? So we're going to talk about some tools and themes that are common when you're dealing with positive functions, and hopefully in that context you will see why we think this curve integral thing is so special. So the first thing that you can do, if your positive function is, and that region is not one of the curvy things that come from the amplituhedron, we'll come back to, you'll find that I actually love these shitty curvy regions just as much as the but for now, imagine that you don't have to deal with it. And f is some rational function from r plus to the m to r plus. Then in this context, you can do optimization. And this is at infinity. Because if it's a function of some positive variables xi, then it's well defined to replace xi by e to the lambda little xi for real xi, and take this limit as lambda goes to infinity. And then what this tells you, and I'm pretty sure many of you in this room, if not all of you, have seen this before, the result of this is a piecewise linear function of the xi's. So this is linear, and it's called trop f. It came from toric geometry. Or rather, e to the exponential of trop f tells you, is as you move around in your r plus, so your positive orthant, then what terms in your rational function f are dominating? So if you imagine that f is just a polynomial, then it's telling you at each point as you move around which monomial in the polynomial is biggest. And so if you go out to infinity in that direction, that'll be the monomial that dominates the polynomial. Okay, so it's a simple idea. And this is something that we can apply in two contexts. So context one. So suppose we have our Feynman integral again. So it looks like this. 1 over u to the mu. Mu is usually d over 2. And then f over u to the omega. So if you call, and it's very important that S is in the Euclidean region. And I don't know how many of you are super familiar with this, with what I mean by this. Is it clear what Euclidean region means? Well, would someone like to define the Euclidean region? Okay, I'll tell you then, since you insist. So it's the region where, so F is some, it's, here's a prototype of F. It could look like S3 alpha 1 alpha 2 plus S1 alpha 1 squared plus other terms like that. So in this case, this is some approximation of the F for a roll with masses. And in this case, you have a quadratic form on the alphas, which are the Feynman parameters, right? Remember where we integrate our Feynman integrals over the positive projective space or over the positive orthant in the alphas. And so this is a quadratic form in the alphas, and S is in the Euclidean region if f of S is bigger than 0 for all alpha. In other words, if the quadratic form defined by the S's is positive. So you can already see in this example that that's going to be a curvy thing, right? Because if I write down the matrix, if I write F as alpha 1, alpha 2 times a matrix that looks like S3, S1, some other things in the S's, alpha 1, alpha 2, then F being positive on the whole region means that this matrix is positive determinant, okay? Which is a quadratic condition on the kinematic variables that the answer is written in. Okay. So we're in that region. And in that region, F is positive, U is positive. So in particular, V, which is F over U, is also positive and non-zero everywhere inside this positive cone where alphas are positive. And then this is not stuff that I do, but it's stuff that Berinsky and Panzer and Smirnov and some people here and lots of people have thought about. You can replace, so if you call U TR e to the trop U, so in other words, this is the thing that point, then you can rewrite this as 1 over U trop to the omega V trop to the omega times the ratios, U trop over U, V trop over V, And this looks like you've made your life worse, but you've secretly made it better. The two applications. I'll applications on this board. From up there, you can see. I can't see it from here. Okay. So the two applications are if you want to quickly check. These are Berinsky's main applications. If you want to quickly check that this integral is finite, then it's a lovely fact that u trop is above and below. Okay, it's obvious that u trop is smaller than u. But it's not clear that it's also bigger than times u, right? But anyway, it is. So this is some nice finite function, and if this is a finite integral, then you'd better hope that setting that whole thing to 1, if you just replace it with 1, then you can check if the integral is finite by doing a much simpler integral only involving the tropicalized u's. But then there's another thing that the finding is useful for. They're finding it useful for evaluating, because this is a simple function, but it's 1 over that function, 1 over v trop. It's blowing up in the areas where the contribution of the integral to the final result is biggest. And so you choose the points you want to numerically sample over, you're numerically integrating, you can do it more efficiently, and you can get a better approximation more quickly by sampling where this blows up. Okay, so that's called tropical sampling. It's a computer technique. And I'll mention on my wish list that you can do that for other things, like string integrals and full amplitudes as well. And it would be very interesting to see what comes out of that. That's context 1. Context 2 is strings. So we don't normally think, I now normally think of strings this way, but traditionally we don't normally think of strings as being intimately related to positive functions on codes. And it's an amazing thing that they are. And so when you have a string integral, it turns out that you can write it as, let's save little y for later. So let's have some big y, and then we're just integrating over the region where the big y's are positive. And there's a surprising fact, which is that your string amplitudes that you care about can be written as rational functions of the big y's to alpha prime si, where si is something like either p1 p2 squared, or the whatever we, when you have p1 plus p2 plus p3 plus p4 squared. What do you call that? Range? Anyway, so whichever variables you're using. Yes. No, for all genus and everything. Yeah. And you can, I'll clarify much more in response to your question in just one bit. But for the moment, I just want to point out that having done this, given that it's possible to write whatever string integral you care about this, the alpha limit immediate because of tropicalization, because these functions f are now written as rational positive functions on the orthant, and because the integral is now over the orthant. So here, for example, is the beta function written this way. It just has one variable y, and then it looks like 1 over 1 plus y to the, say, s, and y over 1 plus y to the, say, t. And when you take alpha prime to 0, so if you take limit alpha prime, let's say the dimension of the moduli is m, alpha prime to the m, in tree level, m would be n minus 3, right? So for a disk integral, your moduli space is n minus 3 dimensional, and you would have n minus 3 capital Y's. But in general, you have more than that when you have loops. It doesn't matter, though, for the purposes of this application. So you have that measure, and then e to the sum alpha prime si f of y. And by replacing y with yi with e to the little yi over alpha prime, you get this upstairs, yi over alpha prime. This becomes d to the dm little y. The alpha prime has been absorbed by that change of variables. And then you're taking this limit. Okay? And what is the answer? Well, alpha prime to the 0 and f to the thing is just going, this combination is just that we wrote before. Right? F is some rational function, and when I take the limit, what happens is that the string integral becomes an integral now over r to the n, so the full vector space, times the tropicalized linear functions, f, that you got by tropicalizing your formula for the string integral. Okay, so we'll be, that leads me on to talk about the parameterizations that allow you to do this for all integrals over Teichmüller spaces. And you should think of this as being the kind of integral that you want to do if you're doing open string theory. But with any number of trace factors and any number of genus and any number of trace factors, genus. I think that's it, actually, trace factors or genus. Okay. So the thing that was different trick. Yeah. And what's interesting, as I will say right now, when you have these, when you have this moduli space, it turns out that you can write a bunch of functions on this moduli space, which you should think of as being related to cross ratios of hyperbolic lengths. So if you think about, if you had a hyperbolic metric on a surface, then the metric defines these lengths, which you have to recognize at the boundary of the surface. Those of you who have ever looked at this will recognize that this is a natural thing to do in that context. But this is not a rational function of anything, no matter what coordinates you're using. This is it's a function of your coordinates, whatever you're using, but it's not a rational function. So uy, it turns out, is a global function on the moduli space, which is positive, for one. But this is positive as well. But it's not just positive, it's also rational. And this is the surprise. Oh, it's not just rational, it's also positive and rational on the positive orthant. Okay? Which means that if, And it's the existence of these functions which underlies um, uh, the, the details that justify Andre's talk from earlier. And that means that if you're doing some integral, for example, if you've got a torus, then normally what we do is we have this measure d tau over the imaginary part squared, and then you have some function which has some modular properties. And if you're integrating over just the moduli space, then you have to mod out by the mapping class group, and that means you end up integrating over some region. If we just ignore the mod out by the mapping class group for a second and focus on what happens to the measure, we can pull back, assuming that f can be written as a function of these u's. I'll show you an example of that in a second. And when you pull back such an integral to the cone, it becomes, once again, of this form, where now the u's are rational functions of the y's, and f will use. And in this form, you have the ability to tropicalize this formula, which you time to zero limit, or you could use it maybe to try and get a better numerical approximation for this integral by using the Berinsky trick of using the tropicalization of this integrand to focus computers on which areas in this orthant contribute to the integral. Okay, so I not only haven't done that, but as far as I know, no one's done that. So I'm putting that on my wish list of things that I would like to see soon. So so tropical approximation for strings. This is for bosonic string integrals, and I'll show you one example in a sec. Yes. So in general, and in particular in this example, the relationship between tau and the y's is, well, there's a map, but to define it, I've only ever done it for the torus, and you have to basically the map involves taking discriminants of it's the solutions equations. Like, yeah, I mean, but even if the map from writing the moduli of the torus in terms of the tau or the complex structure, the map from that to writing it in these coordinates, it's the difference between hyperbolic point of view. It's kind of a extremely complicated thing to describe that map in general. But the reason that there are two reasons why I know how that these parameterizations are true. The first one is that it's related to the Fock and Goncharov presentation of Teichmüller spaces, and then the second picture we have is one that I've been working on more, which is its related representation theory of algebras that are related to. Yeah. 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 The problem. So we tried, and the problem is that when you're doing hyperbolic stuff, you've got all of these regularized lengths, and somehow the natural metric, the natural coordinates don't go over nicely to give you rational functions because you're doing all this stuff with e to the lengths with cutoffs. I would love that if there was a picture like that. Yeah. It's only obvious once you've gone through the long road to start recognizing where your modular functions are. So here's an example. Before loop integration, there's a bosonic integral associated to the closed string. You have two open strings on two different spaces, propagator in between them. Right? That integral has two variables, and the way that you write it when you're in this point of view is product of some nice rational functions to L squared plus P squared times product of the same rational functions, but now with these exponents, times product u n tilde to n squared. Now, so we've got, and these give you a presentation of things that you start to recognize. So these u's are related to curves that go like this. These are the same curves that appear in the Selberg formula for giving the determinant of Laplacians on Riemann surfaces. And this function ends up being something like 1 minus xy to the n product, or plus, I can't remember, which is the eta function. This gives you something like the Jacobi times 1 minus xy to the n times x product up to prefactors, also involving the eta function. This is from the Jacobi, whatever it's called, theorem representation of, is closely related. It's closely related to the Jacobi product formula for the Jacobi theta function. So that's when you start recognizing it, but in general, this is not a trivial thing. So it's not like I've just used different coordinates by starting from normal string theory. There is some non-triviality here that this integral eventually ends up giving you a regularized integral over the string moduli space. But looking at this formula, we could also say you but it's in the same way as when you're doing normal string theory, you can integrate L. This function is xy, and so you get a 1 over log type thing from the Gaussian integral of the loops. And then you can tropicalize that formula as well. Right? So if you do the loop integral, then you tropicalize by setting alpha and send alpha prime to 0. Then you get a formula which looks like integral dy to the dimension of the moduli space times some positive tropical function on the positive orthant, and that corresponds to the loop, to the amplitude of the quantum field theory that you get by taking the alpha prime to 0 limit. Now, that means that we have formulas for the amplitudes of a whole bunch of theories written as positive tropical functions of the positive orthant. The information about the yeah, so yes. So these, I could have put a different exponent here, which is related to what you would think of from the CFT point of view as choosing the dimension of the target spacetime. Obviously this, right, yeah. But all of this stuff goes away in the tropical limit. The reason is that this type of curve, so you imagine that I drew a closed curve like this around the A cycle of a torus. Then, or around, no, let's not do that. Let's say it's around 2 points like that. Then this is not quite at the boundary of the moduli space, because it's always a bit longer than this curve, okay? So all of these cross ratios are eliminated by the tropical limit because they're not the functions that define the boundary of the moduli space. And this is something we understand. So you have formulas now of this kind. This is at any order in say a colored scalar theory, which manifests. So this is where Andre's functions from earlier live. So alpha here is trop of u. U is this nice rational global function on the moduli space. And you have a formula like this for the integrand. It may be, there is a small novelty here for people who've worked with integrands for a long time, that it doesn't matter if you're doing a non-planar color structure. This is still perfectly well defined. And the integrated version, which is also an integral over these lowercase y's, looks exactly like the formula we had before, except that these are now positive functions. And just as before, our amplitude at all, for all color structures and whatever, is always dependent on some kinematics, which also appear in this F. And there is also a Euclidean region, which also where this F, as a tropical function R to the M, is positive everywhere for certain choices of kinematics. So A and I are both positive functions, again, all positive functions. I was going to say something about, I have no idea when I started or anything. 10 minutes? Wow. Okay, so I better add more things to my wish list. So a second wish list item, realizations of some functions to get this presentation, group integrated amplitude theory. And now you might want to take tropicalizations of tropicalizations, because you might, like Berinsky, be in approximating this integral. So trop of trop for both the study and the approximation of partial amplitudes in colored theories is one thing on my wish list. And I should also say that if you want to have some colored theory with some number of flavors, or any interaction Lagrangian with higher interactions and so on, then it's given by a form, but with another positive tropical function here, which Andre was calling n, so I'll do the same. N, you don't need to know about a Lagrangian to define it. All this tropical function needs to do is behave properly at infinity. Because if you think about, for example, the moduli space associated to this world sheet, so that's one factor, two open strings with, that's a two-dimensional moduli space. Here it is. And the positive functions on it break up into these positive linear functions are linear in different regions in this two-dimensional space. And this n should behave nicely as you go off to infinity in any of these particular directions, because those particular directions correspond to stretching to a boundary of this space. So you could have a curve. This is one of the, in this picture, it's easier to see why they spiral from the hyperbolic point of view. So you could have a geodesic representation of that curve, and you go off in that direction, and then you cut the surface open, and it becomes a disk. So when you go off that direction, it's clear in this picture that projecting through this vector to see what the cone looks like at infinity in that direction, you get just this cone and that cone. That's another thing that's, I gave a 1-hour talk on that earlier this year. It's so interesting that knows about the boundaries of moduli space. The details are very interesting. But the point is that this n, when you go up there, should give you the same n for a disk. Okay? So precisely because we have a positive parameterization, we know about boundaries. And this allows us to write down functions for the integrated amplitudes for every single Lagrangian for a colored scalar theory. It also allows us to do another thing, which is compute, for example, asymptotics of, for example, the L loop vacuum amplitude. So if I take the integrand for L loops vacuum diagrams, and I take L to infinity, the positive parameterizations make manifest the asymptotics of that in a way which is different from the usual construction using matrix models. So in fact, these types of positive integrals generalize matrix models, so it would be great to see sort of generalized positive matrix models. Starting from examples like these integrals. The third thing that I probably don't have time to talk about is that this picture, because the moduli spaces recurse into each other, so you have this picture that at infinity, this moduli space becomes this one. Similarly, this moduli space, the one we talked about before, when you so you're making it cross, then what that corresponds to is breaking open. And so in that boundary, you also get back to here. And when you take that into relations for any scalar interaction Lagrangian, the motivation theory. This is something which in the planar sector becomes especially efficient. So you can recurse in the planar sector using recursions that are entirely based around these, what happens when, to these functions when you go to the boundary. Okay. So, but this is, I didn't really want to talk about all of that. I really, really wanted to talk about how I love curvy regions. Okay? So all of this, and I have 5 minutes to tell you about how much I love curvy regions. So all of this magic that allows you to write down string integrals in a way that's purely rational and easy to compute is based on functions that, well, I've erased it, but functions that are rational on cone. But the results are also positive functions, but they're not positive functions on rational cones. They're not positive functions on orthants and stuff. And it's in that context that normally, you know, when we have a function I of x, which is positive on some polyhedrally defined thing, So if that's a polyhedron in projective space, it's the same as a cone in the vector space Rm plus 1. And then there's just this obvious this thing that is now famous amongst certain parts of amplitude world, formula for this type of canonical function of this polygon, polyhedron. And my question is, are there similar formulas for curvy regions? And I'd like to just mention that there are examples of similar functions for curvy regions, similar formulas for curvy regions. And these come from the theorems of Alex Scott, I think, and Alan Sokol, who's the guy who did that hoax with the humanities journals. So they have results which allow you to see that, for example, if you wanted the canonical function of a conic, so earlier we saw an example of a Feynman integral, which is positive. So we are interested in these functions that are positive inside conics and blow up. Then this is given by a formula which looks like I of z, but you think of z as being related to a positive definite matrix. This is positive definite inside the circle where z has homogeneous coordinates. And then the sort of canonical function on here is 1 over determinant of this, and that's given by this beautiful integral over the dual space of positive semi-definite matrices, a space that comes pre-given to you with a nice measure, and then the thing you integrate, sorry, I'm running out of space, bx, okay. So you integrate e to the minus trace bx, which is the natural product on positive semi-definite matrices. In general, you don't integrate over the whole space of positive semi-definite matrices, you integrate over the dual space because you start by looking at some, for example, circle with a line or 2 lines or 3 lines. And this then is the intersection of some positive, the space of positive definite matrices with a plane, and you get a dual geometry. And so for, the integrated amplitude, the Feynman integrals themselves for a specific graph, all of these are examples of things that come from positively parametrized integrals, but whose results are also positive functions, but on a geometry that we really struggle with a lot of the time. These geometries are called spectrahedra, and these formulas are called I don't know these formulas really have a general name. Someone called them positivity certificates, which I like. So maybe we call it that. So positivity certificates for integrated amplitudes. And for those of you who are interested in knowing some of the buzzwords associated with that, the derivatives of these types of functions show you that they're sort of concave functions. So not only are they positive, but they blow up at the boundary, but they look like this in the middle, right? And so monotonicity and complete monotonicity is this other word associated with that. And yeah, okay. So that's my wish list, and some of you are working on things related to this, and so if you could help sort of answer my wishes, then let me know. So the point is, Well, that's why I put it on the list. Well, if you think about computing something like integral dm e to the minus g trace m, and you're looking at the what you end up doing is you count loop ribbon loops. Surprisingly, this is something that's very easy to do when you have these formulas, string, positive string curve integral formulas. You can also do that counting. So, and you also get the same answer. There's some asymptotics involving L and e to the L. But in general, some the L. So why these two things? Especially because is way more is in principle more general than these integrals. So, yeah. But maybe that's a hard problem. It could be as hard as this other problem. From the complex presentation of the moduli space to the rational one. But if there is a link, I'd like to know what it is. Not as far as I can tell. No, I mean, not on my side. Yeah, that's right. Yeah. So I'll tell you that for just knowing these tropical functions do know about the closed propagators. So for example, I don't know, we could take, here's the Riemann sphere, and then I can put some punctures on it. The closed propagators, or the closed string propagators, correspond to boundaries of the moduli space given by closed curves around those punctures. The problem is that in the vector space, so here we are back in R to the M, after I've tropicalized my positive parameterization of the moduli space, each of these boundaries, little y. Yeah, so I start with big Y going from 0 to infinity, and then a global presentation of the moduli space, which includes... No, so go back to theory. We have a parameterization of the moduli space in terms of u big Y. And then to picture the combinatorics of the moduli space, I look at the regions of R to the M of linearity of the functions that you get of little y that you get by tropicalizing big U. Okay? So for example, in the disk, you take your tropical functions, you tropicalize them, and one of them is positive on that side of 0, and the other is positive on that side of 0. That corresponds to two degenerations. In general, that happens here as well. The problem is that degenerations that also, sorry, I drew that wrong, that involve, so you have degenerations relating to these curves, which correspond to going to a boundary of this labeled by a vacuum graph with 1, 2, 3, 4 loops. Sorry, 1, 2, 3 loops. And those, in this space, are full dimensional cones. The boundaries that correspond to just pinching a couple of these closed string propagators are lower dimensional. So in this picture, here's a one-dimensional cone. And they're not just lower dimensional, they're also separated from each other. Okay? And there's an action of the mapping class group, which I haven't described, which you should also think. And so the problem is not that I don't know where the closed string propagators are in the positive parameterized moduli space. The problem is I don't know how to integrate over them in a way that isn't stupid. or in other words, in a way that allows me to take advantage of having a positive parameterization. Okay, because the lower dimensional cones that don't talk to each other. I can show you some pictures of what that looks like in examples. But that is the nub of the issue.